Okay, function folks, part 2 of the 3.5 video is taking up this what y equals tan theta looks like, and hopefully you're able to fill out this chart in class. I hope you used exact values like this, and remember this is from the from the chart. I just read off the tan spot. So the tan of 0 is 0, the tan of pi over 6 is 1 over the square root of 3, and there were reasons why we remember this. How we get the rest of the table, of course, we can kind of use the cast rule. These are the acute angles in here, but then in the second quadrant, right, once I cross the pi over 2 threshold, I'm in the second quadrant, and then the tangent becomes negative. Only the sine is positive there. And remember, the whole thing about this chart is the related acute angle is this, has the same number part with a different sign depending on what the related acute angle is. And of course, it's easier in radians because what the denominator of the fraction is gives me what the related acute angle is. And so it repeats this pattern, negative in this quadrant, and then when it passes over to the third quadrant, it's positive again, and then negative. Some weird things about tangent, though. We have some spots where we get an error message. It's undefined. And so that's going to look strange when we start looking at the graph. And that's what the whole idea of this was to see if we could come up with the trig graph. And I'm just going to plot these points, right? This is the theta axis. 0, 0 is right there. Pi over 6 is this first tick, pi over 6, and then that's about 0.6, and notice on this scale maybe about there. Okay, you got to be careful here. Pi over 4 is actually halfway to pi over 2. This is pi over 4, which is 1.5 ticks is what we would think of it, and it's at 1, so it kind of goes right there. And then square root of 3, I put that into my calculator, is about 1.7. That's there, about 1.7. 1.5 would be there, 1.7, maybe about there. And then something weird's going on here. It's undefined there. So maybe I'll just put U here. What happens? What do we know about what happens when it's undefined? Especially when it looks like the graph is doing this sort of thing. Looks like an asymptote, doesn't it? And that indeed is what happens as theta gets closer and closer to pi over 2, the tangent goes bigger and bigger. And if you don't believe me, find the value pi over 2 and go a little bit lower than that and see how high the tan is. Okay, dandy. So that's those values, and we keep going. So just a little bit on the other side of the asymptote. It'll be interesting to see what happens. It's negative square root of 3, which is negative 1.7 again. So here, negative 1.7 is about there. And then 1, trying to make fat dots here. Then 0.6. And then by pi, it's 0. And this pattern starts repeating, right? Because then it becomes positive. So then it's kind of this piece all over again. 0.6, 1, 1.7-ish, and then another undefined there, another asymptote. And in fact, this is going to give us the shape of what the tan graph does. It repeats this pattern. And so this piece is down here. Now, you might be wondering, do I have to remember all these points? No, just like the sine graph, we're going to remember important points. That's an important point. That's an important point. Of course, the asymptotes are an important point, and so on. Important point, asymptotes, and so important point, halfway between, I get a 1 or a -1 in this case, and then it goes through like this. On this side, every 3 ticks, I get an important point. Or, whoops, I blew that. I wonder if I could just slide her over. Hopefully you didn't copy that, right? And negative pi goes this way. Halfway in between is my -1 right there, or +1 if that's the case, and so on, and so on. 1, 0, asymptote. Beautiful. This is the graph of y equals tan theta. And hopefully you got something that looks like that. And hopefully you're able to reproduce it only using those few facts. I want to, we'll finish this as well. The period is, so shade in, color or shade in one period of the curve. Well, when does it start copying itself? Well, if we start here, when does it start copying itself? Well, it's going up and on and up. Asymptote going up and on, right there. Right there is one piece. You say, well, it looks like this is one piece. Yeah, that's true. You could think of this section right here. I wonder if I can, yeah, this section right here as one piece, but it doesn't matter. The whole idea is how often does it start repeating? Every pi, right? This is pi units right there. What's the maximum? Remember, the maximum of the sine and cos was both 1. Well, there is none. It keeps going forever. What's the minimum? Keeps going forever. What's the domain? See, we're used to writing XER. Any real number is the domain for trig functions, but not for tan. And in fact, we know that x can't be those asymptote values. Pi over 2, 3 pi over 2, 5 pi over 2, and so on. There's an infinite number of domain restrictions, domain holes for the tan graph. What's the range? Well, let's see. What shadow would I have on the y-axis here? Well, all of it up, all of it down. Y can be any real number. And maybe you notice that messing around with your calculator in grade 10, that when you took the tan of a value, it could be anything. You take the sine and the cos, it's going to be between 1 and -1. The tan, any real number. What are the x-intercepts? 0, pi, 2 pi, and there's a pattern going on there too. Pi, 2 pi, and actually those tan has all the same x-intercepts as the sine graph, and we'll talk about that shortly. The y-intercept is 0 right there. Anything else that I wanted to say about that? Nope, that's all I have to say about that. But, oh, no, there's another thing I want to mention about the tan graph. And this is connecting to some stuff you already know, right? If I have the sine graph and the cos graph, I do know that tan x, and this is one of the only trig identities you learned last year, was sine x over cos x. We've talked about this only about 100 times already this year. But remember back to unit 0, we talked about operations on functions. And in fact, to get new functions, all I would have to do is take the distances and do whatever I need to do with them. So here, sine is the red one, green is cos x. If I wanted to get tan x, I could just divide. For each value of x, I could go along and take the red output value divided by the green output value. So let's do that. Red divided by green, 0 divided by 1, well, that's 0. The spot where they cross is supposed to be pi over 4. It's not that accurate, but a number divided by itself, 1. 1 divided by 0, you can't do that, right? You can't divide by 0. That's where I get my asymptote. Moving on, I have a number divided by the same distance but negative. Same distance here, right? That's the same distance but negative. That's going to be -1. Red divided by green. 0 divided by 1 is 0. There's two numbers, the same value, right? That's the same value. Number divided by itself, even if it's negative. Negative divided by negative, +1. And yep, I'm going to have the same sort of thing. -1 divided by 0 is undefined. There's my asymptote. And I can build the tan graph using what I know from operations on functions. Same thing over here, positive and a negative. Distance is the same, going to be -1. 0 divided by 1, 0, and so on. Beautiful. So even if I forget some of the points, where it starts and so on, I can get it by doing a quick in my head a division. However you think of it, however you remember it, this blue one, add it to your graphs of graphs that you need to know. Now you need to know 3 trig graphs. And then in the next video, part 3, we'll be talking about 3 more.